Hey there, YouTubers! Hi there, Dr. Sheep here. Welcome back to the physics video. Today we are redoing a classic series of mine on Newton's 3 laws of motion. Even though one of these videos has over 900 views as of the time of this recording, maybe this entire series will get better views than that series. A boy can dream, can't he? Anyway, if you watch my videos religiously, then you have already seen a much shorter version of this video. I will be doing this for each of these videos to better accommodate different viewers' viewing styles. You can thank Phil for that idea. Anyway, on to why you came here in the first place, which is to listen to me overly explain Newton's first law of motion multiple times. Newton developed his laws of motion in 1686. And since then, we have not been able to throw a ball in the air and not have it come back down. Unless, of course, you're Phil. Make sure you check out my series on energy when you're done here. Anyway, jokes aside, Newton's first law of motion states that an object at rest will stay at rest, and the object in motion will continue to stay in motion unless acted upon by a force that is not already cancelled out. We'll get into what a force is in Newton's second law. For now, all you need to know is that a force will either change a moving object's direction, change a moving object's speed, or move an object that is not already moving. Matter's tendency to be sticky in this way is called inertia. Thanks, Bill Nye. Inertia is a property of matter, and Newton's first law is the law of inertia. So can we actually see Newton's first law in action? Well, you're watching it right now. My whiteboard is currently being pulled towards the center of the Earth by Earth's gravitational pull. However, screws are preventing that. The screws are applying a force equal to that of the Earth's gravitational pull. This results in the net forces acting on the board to be zero. If I removed the screws and I had two big people holding it, and then they were to let go, the board would fall. Therefore, the object is no longer at rest and is now in motion until it hits the floor. However, things at rest and thinking about them moving is boring. So let's actually make things move. This is an ice cube on a tabletop. It is at rest and won't move unless my hand gives it a little push. Then it keeps going and going and going until it melts, hits something, or the universe ends, and every last bit of matter is converted to Hawking radiation. This is true as long as no forces are acting on it like gravity, light, or friction. And good luck trying to find a place in the universe where you can avoid all of that, because it is impossible. Now it's time to supersize. Whew, it's been a long time since I've said that. And there are a lot of new people subscribed to the channel, which you should do as well. Anyway, it means I'm going to make the experiment bigger. Now, according to Newton's first law, the couch should keep going when I push on it. But it doesn't. The ice cube was clearly faked. It came to a stop, just like the couch. But why? I would do the top from the bottom up transition, but I sustained some rug burns when my roommate tackled me because I locked him outside, and so now I can hardly bend my knees. Well, as I alluded to earlier, because that's actually a pretty good transition from how I got the rug burns. Friction is the pain in the butt, or knees, of every physics student ever. The ice cube has a layer of water between the ice and the surface of the table that limits the amount of friction between the surfaces. This allows the ice cube to keep moving much further than the couch. The couch has a very grippy bottom, and the carpet is also very grippy. This prevents the couch from continuing to move after I apply the force. Now there is one more experiment to do that demonstrates Newton's first law. I am moving at a constant speed in one direction while holding the ball. Therefore, the ball is moving at the same velocity I am. When I throw the ball in the air, it keeps that same velocity.
So when gravity pulls the ball back down, it lands back in my hands. This works at even higher speeds. Just have someone drive down the highway at legal speeds, and you throw a ball in the back seat. And as if you're not even moving, the ball will come right back down and land in your hands. Actually, that gives me a good idea. Let's supersize, shall we? As you can see, Newton's laws remain even at higher speeds. However, because of air resistance, if we were to go faster, the ball would leave the back of the truck. In an environment absent of air, or a vacuum, the ball would come back down, no questions asked.
Okay. I think Phil was right when he said that you can only explain each law so many times before it gets really repetitive. Leave a comment if you have any questions regarding Newton's first law. Phil and I will try our best to give you correct answers. Either way, go watch the second part in this series on Newton's second law. But in the meantime, I would like to thank you all for watching. Please like, comment, share, and subscribe. New videos every other Friday, noon Central Time, and good night. Subs for trees, subs for trees, subs for trees, subs for trees. Oh, you're still here? I thought I told you to go home. Oh, you want more? I'm flattered. Check out the playlist. If you want exclusive content, check out my Instagram, Dr_Sheep_YouTube. That's all lowercase. If you want to help the earth, subscribe. When I reach 100 subscribers, I'm going to plant 10 trees. If you feel that's too small, then check out my channel chart where I lay out even bigger goals. Finally, stick around for the next 20 seconds to give me that sweet watch time. Bye.